Have you ever pondered the intricate mysteries of the universe, the fundamental forces that shape our reality, and the particles that constitute our very existence? From the smallest subatomic particle to the sprawling galaxies, everything in the universe is woven together in a grand tapestry, a cosmic symphony of matter and energy. Since time immemorial, humans have sought to unravel this cosmic puzzle, to decode the fundamental laws that govern our universe. In this quest for understanding, we've come across a revolutionary idea that challenges our conventional wisdom and redefines our perception of the universe. Enter the theory of strings. This radical theory proposes that the fundamental constituents of the universe are not point-like particles, which has been the prevailing viewpoint for the better part of the last century. Instead, it posits that the basic building blocks of the universe are one-dimensional strings, entities that vibrate at different frequencies. Imagine a violin with its strings. Each string, when plucked, vibrates at a unique frequency, producing a distinct note. Similarly, according to string theory, each string in the universe vibrates at a unique frequency, and these different frequencies give rise to the diverse spectrum of particles and forces we observe in nature. These strings, as per the theory, exist not in our familiar three-dimensional space, but in higher dimensional spaces that are beyond our everyday perception. By embracing these exotic mathematical constructs, string theory attempts to reconcile quantum mechanics and general relativity, two pillars of modern physics that have resisted unification. The implications of this theory are profound. If validated, it promises to provide a unified description of all fundamental forces and particles, a grand theory of everything. So, instead of particles, we have strings. A simple shift in perspective, yet it promises a radical departure from our conventional understanding of the universe. The idea of string theory didn't just pop up overnight. It was a product of decades of scientific exploration and mathematical innovation. In the latter part of the 20th century, physicists were grappling with two mighty pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, and general relativity, Einstein's theory of gravity, were both incredibly successful in their respective domains, yet they seemed to be fundamentally incompatible with each other. This discord was a thorn in the side of physicists. It was like having two different rulebooks for the same game, one for the tiny particles in the atom's realm and another for the vast cosmos. This division was unacceptable to those who believed in a symmetrical and unified universe, and it led to the pursuit of a grand unified theory, a single framework that could accommodate both quantum mechanics and general relativity. Enter string theory, the brainchild of innovative minds seeking to reconcile these two incompatible theories. Instead of viewing the fundamental constituents of the universe as point-like particles, string theory proposed something radical. It suggested that these constituents are one-dimensional strings vibrating at different frequencies. These vibrations give rise to the diverse spectrum of particles and forces we observe. String theory was not just born out of necessity, but also from the beauty of mathematical elegance. It embraced the concept of higher dimensional spaces, going beyond the three spatial dimensions and one-time dimension we're accustomed to. It painted a picture of the universe that was not only captivating, but also intricately complex. At its heart, string theory was a bold step forward. It was an ambitious attempt to unify the seemingly disparate realms of the quantum and the cosmic under one mathematical roof. The theory offered a potential solution to the long-standing puzzle of quantum gravity, the hypothetical quantum theory of the gravitational force. Thus, string theory was born, a beacon of hope in the quest for a unified theory of everything. The allure of string theory lies not just in its novelty, but also in its promise. This promise is seen in its potential to resolve some of the most perplexing puzzles in physics and provide a unified description of fundamental forces and particles. Imagine the universe as a grand symphony, with each string vibrating in harmony to compose the celestial music of existence. Each string, according to the theory, vibrates at a different frequency, giving rise to the diverse spectrum of particles and forces we observe in nature. It's similar to how different musical notes emerge from the strings of a violin, each one unique, yet part of a harmonious whole. One of the most tantalizing prospects of string theory is its potential to reconcile quantum mechanics and general relativity, two titans of modern physics that have, till now, resisted unification. Quantum mechanics governs the realm of the very small atoms, electrons, quarks, while general relativity reigns over the vast expanse of the cosmos, governing planets, galaxies, and black holes. Despite their individual successes, these two theories clash at the extremes, especially when it comes to understanding black holes or the origins of the universe. String theory, with its one-dimensional strings and higher dimensional spaces, promises a bridge between these two realms, a possibility that could revolutionize our understanding of the universe. It's like discovering a universal language, one that can describe both the dance of galaxies and the ballet of subatomic particles. Beyond its unifying aspirations, string theory has also contributed valuable insights to other areas of physics, such as condensed matter physics and cosmology. Its mathematical structures have found applications in understanding phenomena like superconductivity and the early universe, demonstrating its versatility and explanatory power. The elegance of string theory and its potential for unification make it a compelling, albeit controversial, candidate for the theory of everything. It's a promise filled with potential, a journey into the heart of the universe, a voyage we've only just embarked upon. However, every silver lining has a cloud, and string theory is no exception. While the promise of string theory is captivating, it's equally important to acknowledge the criticisms it faces. These criticisms revolve around two main points: the lack of experimental evidence and the difficulties in making testable predictions. String theory, unlike most scientific theories, operates at energy scales that are currently beyond our reach. This makes the task of gathering empirical evidence for string theory a challenging endeavor. The current limitations of our particle accelerators make it impossible to directly confirm or refute the predictions of string theory. This lack of experimental verification has incited skepticism in the scientific community, casting doubt on its empirical validity. In addition to the lack of empirical evidence, string theory also faces criticism for its inability to make testable predictions. The theory describes a vast landscape of possible string configurations, each one corresponding to a different universe with its own physical laws. This string landscape presents us with a myriad of mathematical possibilities, but it also complicates the task of empirical validation. The vastness of the string landscape allows for a multitude of scenarios that may not be testable in practice, thus hindering the theory's predictive power. The debate over string theory's status as a scientific theory is fueled by these criticisms. Critics argue that its reliance on complex mathematical structures and speculative conjectures detracts from its status as a scientific theory. They suggest that without clear experimental evidence or observational support, string theory risks crossing the boundary into metaphysics or philosophy rather than empirical science. The lack of progress in resolving key theoretical ambiguities, such as the selection of a unique vacuum state or the formulation of a predictive framework, further feeds into these criticisms. Despite the allure of string theory, these criticisms point to significant obstacles that it must overcome. Doubts persist and questions loom. Is string theory a scientific truth or a mathematical illusion? As we continue to unravel the mysteries of our universe, only time will tell. The debate about the status of string theory is far from settled. This captivating theory, straddling the boundaries of scientific exploration and philosophical speculation, continues to generate heated debates among physicists and philosophers alike. The main points of contention revolve around the empirical basis of string theory and its ability to make testable predictions. Proponents of the theory laud its mathematical elegance and promise of unification, asserting that its potential to resolve long-standing puzzles in physics and its versatility across various fields underscore its scientific merit. They argue that the lack of direct experimental evidence does not diminish the theory's value, as it operates at energy scales currently inaccessible to our experimental apparatus. Critics, on the other hand, express skepticism about the theory's status as a scientific truth, pointing to its lack of observational support and the difficulties it faces in making falsifiable predictions. They argue that the vast landscape of possible string configurations, while mathematically intriguing, poses a significant challenge for empirical validation. Moreover, they contend that without concrete progress in resolving key theoretical ambiguities, string theory risks veering into the realm of metaphysics. The implications of this ongoing debate are profound, shaping the future course of theoretical physics and our understanding of the universe. If string theory withstands the test of empirical scrutiny, it could provide a unified framework for understanding the fundamental laws of the universe, revolutionizing our perception of reality. However, if it fails to deliver on its promises and fades into the annals of scientific speculation, it could prompt a re-evaluation of our approach to unifying quantum mechanics and general relativity, spurring new avenues of research. As we continue to probe the mysteries of the universe, only time will tell if string theory will stand the test of empirical scrutiny or fade into the annals of scientific speculation.